which one is not the basis? Find the odd one out. And we of course know that with any vector space we can have an infinite amount of bases. Choosing the basis is just a matter of choice or perspective. And here we have 3 bases and 1 imposter. So we need to find the imposter. Let's agree on some things. So if I take a very simple example of a 2-dimensional space, and I take 2 vectors which are linearly independent, which kind of means that they don't cancel each other out, then it looks like if I keep going on this line, and as I go on this line I have the freedom to stretch and shrink, stretch and shrink, then it looks like I can reach any point in this space. I can do the same as well if I just take the negative counterpart of this vector. I move it along this line. Oops, I think I got a bit too carried away here. Along this line, and as I go I can stretch it and shrink it, stretch it and shrink it. And if I'm able to do this, then I should be able to span the whole plane. But if I choose 2 vectors, and I choose 2 vectors for simplicity, which are on the same line, then this new vector does not really add anything to the span. All I can do is move along this line. This is all I can do, because these 2 vectors are linearly dependent. And because they are linearly dependent, I can't unlock this new dimension, which is in these 2 directions, you could say, or you could think about it in this way. So, if you have a space like the space of cubic polynomials, and there is a set that should not be a basis, then this set must have a missing vector. So it must have, a vector that's linearly dependent on the others. In other words, you could say that this vector depends on, or could be described using the other vectors. Now, formally and rigorously, we define linear independence as follows. So if we take this vector, which I'll call vector v1, and take another vector, which I'll call v2, and we scale this v1 by alpha 1, and we scale this v2 by alpha 2, and we get the 0 vector, then, well, the 0 vector is right here. Then this should imply that alpha 1 is 0 and alpha 2 is 0. What does this mean? It just means that the only way to obtain the 0 vector, not the 0 constant, is by scaling this vector v1 down to 0 like this, and scaling the vector v2 down like this. Well, maybe smaller, right? Yeah. So this would be the only way you would obtain the 0 vector. Let's see a non-example. A very simple one is this one. So let's take 2 linearly dependent vectors. Then I can always reach the 0 vector by adding this vector to that vector. You see? So in other words, if the two vectors do not cancel out each other, well, 2 vectors, 3 vectors, 10 vectors do not cancel out each other in some way, then this should be a set of linearly independent vectors. And so, today, with this exercise, our goal is to do the following: to cancel out the basis vectors. Using some scalings, of course. So with some scalings. Let's take a quick look at, for example, the first one. First one has x cubed, x squared, x, and 1. There is no way you would cancel anything out with anything, right? Because when I say cancel out, I mean the following. So I mean alpha 1, let's say, times x cubed plus alpha 2 times x squared plus alpha 3 times x plus 1. How would you cancel x cubed with x squared, or x squared with x, or x with 1? This wouldn't simply happen at all. So it is safe to say that this set will actually be linearly independent, not for this very specific reason. Well, yes, for this specific reason, but I have not expanded it in the way that I should have, perhaps. But this one is a bit more interesting. You see that if we add this vector as it is to this vector, then the x squared will cancel out. And then if we add this, these two vectors, and we add to this third vector, then the x cancels out. And then we add this vector as well, so the ones cancel out. Let me be very specific here by what I'm saying. So what I'm saying is, we take all of these vectors and we scale them by 1. So I make the choice to scale them by 1, but I could also make the choice to scale them by other scalings, each single vector separately. I always have the freedom. So this is what I meant. If I do this, this cancels out, this cancels out, this cancels out. So I get x cubed. But there's nothing in the world that I can scale any of the other basis vectors by to cancel this x cubed, because it's simply not in my toolset. So, well, not precisely why this is a set of linearly independent vectors, but it is a set of linearly independent vectors. And the most interesting one is this one, because this will actually be the answer. You know, surprise, surprise. Because this one has an x cubed, it has the x squareds, and it has the x's. So let's write this down, and let's write it down very rigorously. By rigorously, I mean, we'll say we have this set of vectors. Okay. We will scale each vector by scalar. So I'll scale this by alpha 1. I'll scale the second vector by alpha 2. I'll scale the third vector by alpha 3. And I'll scale the final vector by alpha 4. You know, so some constants. And I'll set this to be 0. And I'll ask the question, would this imply that all coefficients alpha 1, alpha 2, alpha 3, and alpha 4 are equal to 0? Well, let's see. Well, I'm telling you beforehand that it will not be, So perhaps it is a good idea to find the linear combination, the non-zero linear combination that gives us 0. In other words, we should find the linear combination that makes these terms cancel out with each other. So this is precisely what I'm going to do now. Let me focus on eliminating the x cubed here. So I have, let's say I choose x cubed minus x squared. I'll choose alpha 1 to be 1. Why not? And here I have an x cubed. So probably I'll choose, here I chose alpha 1 to be 1. To cancel out this x cubed, I'll choose this alpha 2 to be minus 1. Then I get the following. I get x cubed minus x. I'll distribute this, I get minus x cubed plus x. So they do cancel out. Now I have minus x squared plus x. How do I cancel minus x squared plus x if all I have is this alpha squared, this x squared minus x? What should my choice for alpha 3 be if I want to get a 0 in the end? Yes, the answer is just to take alpha 3 to be 1. Then I have x squared minus x in the brackets. Brackets don't matter because this is a plus. And now x squared goes with x squared and x goes with x. And I can simply choose, alpha 4 to be equal to 0. So the implication is really strictly saying that all coefficients must be equal to 0. But if there's, some vectors that cancel each other out, then this is completely fine. By the way, what this is really telling us is that x cubed minus x is equal to x cubed minus x squared plus x squared minus x. So do you see how if I add this vector to that vector, I'll get this vector? So this is what I mean when I talk about linear dependence. So we have a linearly dependent set of vectors here. We have a non-zero combination that gives a 0. We have a set of vectors that cancel each other out without all of the scalings being 0. And if that's convincing for you, then that's amazing, because this is really all you need to do for the exercise, for this very specific exercise. And I mean, in a practical context where you would like to find the solution to the problem. Here we were testing with this set of vectors. We were able to find a non-zero set of scalings which give us 0. Going back perhaps to the point that I was talking about earlier about the linear independence of these vectors. Perhaps I'll do one example just for the sake of illustration, and maybe you can do the same with the other ones. So I'll do the simple one. How do I show that this is actually linearly independent? The way I would do this is I would take, well, I don't need to copy and paste this. I would take, scalings of each basis vector. And I would set this to be equal to 0. These are my scalings, and this is my set of basis vectors in green. Now, if this is 0 by comparing coefficients, then clearly the coefficient of x cubed is equal to 0. the coefficient of x squared is equal to 0. Coefficient of x is equal to 0. And the coefficient of 1 is equal to 0. Because everything is 0 on the other side. I could also write x cubed plus 0x squared plus 0x plus 0. So that's also perhaps some convincing for you. So if you want to check that your set of vectors are linearly independent, this is precisely what you should do. You should write down your arbitrary scalings, and you should set your you should set this linear combination of your vectors to be equal to 0. Not 0 in the sense of the 0 constant, but the 0 vector. And when you do this, you should get this implication. Well, these 4 implications. As an exercise, I would recommend you do the following. Exercise. Check the linear independence of this set of vectors. The way you would do this is you would take alpha 1 of this set, you would take alpha 2, this thing, you take alpha 3 of this thing, and alpha 4 of this thing. The numbers are arbitrary. Don't focus on the numbers. There's just, when I say alpha 1, alpha 2, alpha 3, alpha 4, they're not important. I'm just saying, so some constant, and some constant, and some constant. And set it to be equal to the 0 vector in this format. And let me know if you get the implication that your alphas should be equal to 0. If you want to take this even one step further, you could even do it. You could do it for this set of vectors afterward. You're bored and you don't have anything else to do. So this is how you check that something is linearly dependent or linearly independent. I hope this was a comprehensive tutorial in that sense.